Think about it. If every point is an axis unto itself, that wasn't the case in the previous thing. Every point is a two-dimensional point. If I put every point as an axis into itself, at that point you know for sure that it can be separated. So there is an asymptotic guarantee that everything can be separated if only you blow up the dimensionality. The question is, sometimes you might be able to blow up the dimensionality to a much lower level and still be able to separate them. And second of all, it's extremely silly to first blow up the dimensionality, then separate, and then come back yourself, because that would essentially do all the work. Instead, there are techniques such as kernel SVMs, which do this whole thing in one fell swoop, which is why they have become popular. Okay? So, in essence, what they will then do is they will come up with specific kinds of these things called kernel functions, which if you have x1, x2, a polynomial kernel function of dimension 5 will consider all 5-dimensional polynomial, not coefficient, 5-dimensional polynomial terms. So in a 5-dimensional polynomial, what are the terms that will be there if you have x1 and x2? x1 plus x2 power 5. Remember your binomial theorem? x1 plus x2 power 5, you'll have x1 power 5, you'll have x2 power 5, you'll have x1 power 4 times x2, you'll have x1 power 3 times x2 power 2, etc. Right? And for each of these terms, you have a dimension. And then for everything whose xy values you know, you will be able to compute these new terms. And it turns out, and then check if in fact it is linearly separable in that higher dimension. If so, then you can come back. Okay? So in fact, as I pointed out, when you do that kind of a thing, for example, this is x1 and x2, and I have a circular data. With inside the circle is positive, negative, I guess, outside the circle is positive. Clearly there is no line to separate this. But if on the other hand, you consider a three-dimensional space, x1 square, root 2 x1 x2, x2 square. Right? That's a polynomial kernel transformation. It's a subspace actually. Right? And in that space, if you actually compute each of these points coordinates in this three-dimensional space, then you will be able to see that there is a plane. And what kernel functions do is they will, in one fell swoop, take you from here to here, find the equation of the plane, come back and tell you what the equation of the plane is in this region. And it will be a curve. Okay? So that is SVMs. Right? So that's one idea. You guys probably didn't hear about it because there's not too much hype about it right now. This is a 90s idea. Nobody listens to 90s songs. Right? We're only listening to 2000 songs. So the 90s, basically what was happening was, it's after 80s, people actually have figured out backpropagation and people were trying to use multi-layer neural networks and they were still not working. And there was this old man called Vladimir Vapnik. He's old now, but I think he was young at some point. And when he was hanging around in Moscow in 1960s, apparently everything happened around the time I was born. He basically, he's a mathematician. Russians basically didn't have computers, so they just have pencils and maybe sometimes paper. And then they would just write stuff on this stuff, and math doesn't need much more than that. Remember Einstein's wife told somebody that my husband doesn't need any hardware, he just needs a pencil and paper. Math is abstract, right? So what he found was, he found the idea of SVMs and kernel machines in 1960s. But whoever expects to look in Russia for good stuff? Right? So we ignored him. We continued doing our own random stuff. And in fact, he was trying to then use his SVMs for doing some cancer diagnosis, that, etc. Who the heck cares? This is Soviet Union, we don't know. And in the 1990s, he was brought in to one of the greatest research facilities in US before it got, it just blew up, which is Bell Labs. Now, pretty much every damn thing that we use today can be traced back to research done in Bell Labs. And people used to Basically, Bell Labs was this was the monopoly of Bell Telephone Company, and they had enough money that they can also support research. Nowadays, nobody supports research. Research is the kind of thing that you do if you have lots of extra money left. Okay, so they used to do stuff without knowing whether or not they'd ever be useful. Bell Labs basically invented transistors. Bell Labs, by 90s is actually a very small place, but they were able to get Vladimir Pavlik there. At that time, actually, it was a great department, principals of AI department, and the labs had a bunch of people who now have basically gone on to different places, including Jan LeCun was there, and then Vladimir Pavlik was there. So he came and he said, "Oh, looks like these people have these conferences. Let me write some NeurIPS paper." So he wrote a paper to 1991 to NeurIPS. It was called NeurIPS at that time. He wrote the paper and 2 rejects. It was a time when there were not that many papers, maybe 7 papers will be submitted. They still said not Vladimir, okay, not his paper. So it was rejected. Then he was looking around and people were trying to do this digit classification. Remember, that was the thing that ConvNets became popular for. Okay, he was doing MNIST digit classification. And people were doing this, and he looked at it and said, this is, you guys are doing it with this ConvNets, it's pretty inefficient, it's nonsense. Why? I bet I can do this much better with this kernel support recognitions. And Corina Cortez, who was working there, worked with him, and they both, and she and he, essentially got state-of-the-art performance on MNIST. With much less training, much less data needed. In fact, the thing is that essentially kernel machines tend to be, when they work, for a problem for which both multi-layer neural networks and kernel machines work, kernel machines are way better in terms of sample complexity. In terms of learning, the difficulty of learning typically is not the computed time. It is the number of examples you need before you learn. Do you understand what I'm saying? The slow learners need a lot more examples, the fast learners need fewer examples. It's not the computer time, it's the number of samples. That's why we think in terms of not time complexity, but sample complexity. And for kernel support vector machines, sample complexity is typically much lower than that for multi-layer networks. And so they rode the wave in 90s. So if you are doing this class in 90s and even beginnings of 2000s, and in fact anywhere before 2013, we would basically say, neural networks, died. Let's talk about kernel machines. Okay, but now Vladimir, basically nobody cares about him. He's been hired by Jan LeCun to be hanging around in Facebook. He's the trophy mathematician, if you know what I mean. Okay, so he just hangs around there. In fact, he wrote a very interesting paper recently that I can send you a copy of. You can read it out if you want. But anyway, that's Vladimir story. Other thing which is always possible, this was done before as well as after, is having multi-layer networks. If you have multiple layers, you're done. In fact, this is what we showed you in these examples, right? If you guys looked at it, you understood that it can be done by both. What is interesting is this. There is a theorem. There is actually a theorem for kernel machines too, but there is a theorem for neural networks that you know that for a single layer network, not even all Boolean functions can be learned, right? But the question is, if you put more layers, at least with one extra layer, we could learn XOR. The question is, how many layers do you put to get more and more functions learned? If you're a computer scientist, you'll put one more layer, one more layer, one more layer, see what happens, until the boss yells at you. Mathematicians have no bosses, they don't get much pay, so they write actually theorems. And what the theorem they wrote, essentially, the beautiful theorem about neural networks, the one thing that you want to remember, is that given any continuous function on your inputs, there exists some neural network with one hidden layer which approximates that function to any level of accuracy. Do you see what I'm saying? You people are surprised at this? This you should be wondering, why the heck do I need deep then? I just need one layer. It's true. Mathematically, you don't need more than one layer if you are looking only at continuous functions. Then you say, then obviously, if the discontinuous functions, maybe you need 250 layers. Now there's a corollary to the theorem. For any discontinuous function in the world, there exists a 2 hidden layer neural network that will solve it. Do you understand what I'm saying? Now you might think, first of all, you might ask, when the heck are we doing deep learning? The thing is that when I say some neural network exists, I never said how many units are there in the hidden layer. Think of kernel machines. They essentially can take a 2-dimensional data, blow it up to infinite dimensions, and then look for a line separating them. So in the worst case, the good neural network that you're looking for might have close to infinite number of hidden layer units. And you can't just say, I search for one hidden layer network with 2 units in the hidden layer and it's not good enough, so I give up. No. You have to consider 2, 3, 4, all the way to infinity. That's how mathematical theorems are like. Okay? Now the only question, and I want to just show you this picture and then we'll move on to the next class, is the only question is, if you wind up having, you at least need one hidden layer, right? Because for every continuous function you need one hidden layer. For every discontinuous function you need 2 hidden layers. Either which way, from the math that we have done, we knew how to do a single layer network. This would be the input, this would be the output. We knew how to compute the gradient updates for that. Now I need to know how to compute the gradient updates when there is 2 layers. Multi-layer networks use 2 layers or more. The interesting question is, for the longest time, for a variety of sociological reasons, people will look at it and say, oh, let's not do this. This stuff is going to get stuck in local minima, and also we don't know how to do gradient descent. Of which the first one is still true, it can still get stuck in local minima, and the second one is false. It turns out that the same chain rule that you used to compute the gradient at the first layer will also work for the second layer. In particular, so this is the derivation. I will either talk to you about it next class, or I will record something walking you through this derivation next class. It's just chain rule, believe me. But the 2 parts I want you to remember is, for the first layer, the weights here, they will be updated using this gradient. And notice this gradient. This is the error, this is the G dash, and instead of II, you have AJ, which is the activation of that particular level. You did all the math and you got that. It looks exactly the same form. And for the second layer, 2, it basically looks in the same form. Okay? And in particular, an intuitive way of understanding this is, you know what the error is at the highest layer, because you know what the actual values are supposed to be. You don't know what the error is here. Most people who started thinking, most psychologists were the ones who used to do learning. Psychologists are unfortunately poor in math. And they would think, we know what the error is here, we don't know what the error is here, how will we figure out what to minimize? Do you see what I'm saying? Turns out that's a stupid question to ask. Because you, in essence, when you do chain rule, in essence it will all work out in terms of just looking at the error and you're taking the derivative of that error with respect to these weights. But if you're a psychologist and you still want to say, I don't care about math, tell me some intuition. Here is the intuition. That's the very last thing I'll tell you. If you have an error here, you need to give the credit of that error to each of these bosons. Okay? Imagine I have an error here. Of 100. This guy has weight 0, this guy has weight 100, this guy has weight 0, weight 0. Who should be blamed for the error at the last level? We didn't start the fight, these guys will say. Because we have 0 weights. We couldn't have caused any error. This guy with the high weight must have caused the error. Let's give all the error to him and deal with it. So in essence, instead of 100, 0, 0, if you wind up having this is 75, this is 39, this is 47, this is 87, I can then essentially divide the error to each of these units in proportion to the weight with which this unit is connected to the error unit. If you say that, and if you're a psychologist, you feel, yeah, there is good stuff going on. In fact, many books would explain backpropagation this way, as if there is some sort of a mystery where you have to decide who to blame for how much, and let's just do this intuitively this way. It turns out that this intuitive definition is also what the math tells you. We'll stop here, come back next class, and continue.